Hello and welcome to this new video. So in the last video there were some typographical errors, but I corrected them and I posted the solution to the exercise of chapter 2 on my website. Okay, so please you can check. And in this video I'm going to start and finish chapter 3. So chapter 3 is about continuous functions, and we shall study in details continuous functions in the course of topology next year. Okay, so because topology is basically the study of continuous functions. So in this video I'm going to be sketchy a little bit, so I'm not going to give proofs. Okay, and please don't worry, I will not ask you about a proof that I didn't give in the lectures. Okay, so I will be sketchy here. Okay, so let us revisit first the notion of continuity that you may know. I just want to, as I did for the sequences, for conversions of sequences, I just want to make a link between the intuitive notion of limit and the epsilon-delta definition, okay, that you probably learned. Okay, so what does it mean to say that a function of a real variable is continuous at a certain point? Okay, because we start defining continuity at the point, and if f is continuous at every point, we say that f is continuous on its domain. Okay, so what does it mean to say that f is continuous at a point x0? Well, you can say that this means that the limit of f of x as x tends to x0 is precisely f of x0. Okay, but what is the limit? So once again, limit means that I can approximate f of x0 by f of x. Okay, so the intuitive idea is that I can make f of x as close as I wish to f of x0 for all x sufficiently close to x0. This is the idea. Okay, it involves the idea of approximation. So what does it mean that f of x is arbitrarily close to f of x0? It means that the distance between them can be made arbitrarily small. So small means that less than any positive number I like. Okay, and it's here that the epsilon comes. So if I can make this less than any positive number, it means that I can make it less than epsilon, provided x is sufficiently close to delta. Okay, so this is the epsilon-delta definition that you probably know. And once again, you can think of epsilon as being the degree of accuracy of the approximation. So if I want to approximate f of x0 up to 9 decimal places, I take epsilon equal 10 to the power minus 9. Okay, and then these two numbers actually have the same 9 decimal places. Okay, and of course I can rewrite this inequality as, so f of x minus f of x0 in absolute value is less than epsilon, means that the difference is between minus epsilon and epsilon, or if you like, f of x is between f of x0 minus epsilon and f of x0 plus epsilon, and same thing for delta. Now this is a neighborhood of f of x0 and any neighborhood of f of x0 contains an interval of this form. So I can rephrase actually this condition by saying that for every neighborhood v of f of x0, I can find a neighborhood u of x0 whose image under f is contained in v. So how do I know that? Because if x is in u, then f of x is in f of u. So f of x is here, so it's in v. Okay? And now, first remark, we can replace less than delta by less or equal, because of course if it's less than equal, and if it's less or equal than delta, then it's strictly less than 2 delta. And same thing here, if it's less than epsilon, less or equal than epsilon, it's less than 2 epsilon. If epsilon is arbitrary, then 2 epsilon is arbitrary. So we can replace strict inequalities here by large inequalities, but pay attention, I cannot put here bigger or equal than 0, it's not true, or delta bigger or equal. So the epsilon and delta should be strictly positive, but the inequality here can be large, it doesn't matter actually. And now, as I said, f is continuous on a set capital A if it's continuous at every point of capital A. Okay? So if I want to write this condition for f is continuous at every point x0. So for every x0 in A, and for every epsilon positive, I can find a delta positive such that for all x in A, if the difference between x and x0 is less than delta, then the difference between their images is less than epsilon. So in general, so the order of the quantifiers here is very important actually. So usually delta depends on x0 and epsilon. Okay. Now, if it happens that I can choose delta independently of x0, so just dependent on epsilon, then we say that the function is uniformly continuous, and we shall get back to this notion by the end of the video. And you may prove actually that all the elementary functions that you know, polynomials, radicals, trigonometric and inverse trigonometric functions, logarithms, exponentials, are all continuous whenever they are defined. Okay, also the ratio of two continuous product and so on. So I'm not going to prove this here. So for elementary functions, continuity, we can prove that actually, but I'm not going to do that here. Now let us, so our first result, actually we can characterize continuity by sequences. So there is an equivalence between the continuity of a function at a point x and the condition of conservation of convergence. So saying that f is continuous at x is equivalent to the condition that if a sequence converges to x, then the image of the sequence converges to the image of f, of x under f. So this is, you can prove that actually. 1 implies 2 is easy if you go back to the definition. 2 implies 1 is a little bit more tricky because you have to reason by contradiction, and I will do that next year in the topology course. Okay, but you may be already familiar with this characterization of continuity, and we used it actually before in previous videos. Now, the first result is what we call the extreme value theorem that you probably know. If we have a continuous function on a compact interval AB, so it's very important to take a closed and bounded interval, because then actually f is bounded and achieves its bounds. So the supremum and the infimum are finite, and they are, so the supremum is a maximum and the infimum is a minimum. Okay, so this is what I mean by achieves its bound. So it takes a maximum value, and not all functions satisfy this property. Okay, so the sup is a max and the inf is a min. Okay, it's very important to pay. Well, we need two conditions actually. We need a condition on f, which is continuity, and we need a condition on the domain of AB, which is compactness. Okay, which is a topological condition. So this is, so most of the results that I will present in this video are topological in nature. So it's better to postpone them to the next year. Okay, so now I'm not going to prove next year. But I have a remark here. So if we remove one of the conditions, so either continuity or compactness, the result may be wrong. So let me give you two examples. If you take the function defined on -1, 1, so which is compact here, by 1 of x, if x is different from 0, and 0 if x is 0. So it's actually two branches of a hyperbola, but finite branches. So they stop at -1 and 1. But as x tends to 0, f of x tends to plus infinity or minus infinity depending on the sign of x. So of course, actually here f is not bounded. Okay, what is the problem? The problem is that f is not continuous, and it doesn't depend actually how do we define f of x at 0. You can put anything here, actually. You can put 1, anything, -1. The problem is that f tends to infinity or minus infinity at 0. So no matter how you define this, it will be discontinuous. So the problem is here is the lack of continuity of f. So continuity is very important to prove that f is bounded. Next example, we have a continuous function, but the domain is not a compact interval. It's the whole line. So this is a bell-shaped curve, actually, that tends to 0 at minus and plus infinity. It's symmetric. It has a maximum value 1 at 0. Actually, this function is bounded, but it does not achieve. It achieves its maximum, which is at 1, at 0, which is 1, but it does not achieve its infimum, which is 0. Okay, because this function is never 0, but the infimum of it is 0. So the supremum, the infimum is not achieved. Okay, so there's no minimum value here. There is a maximum value, but no minimum value. And if you invert this, if you take minus this, you get the opposite result. You get a minimum, but not a maximum. Okay, so it's easy to construct other examples like this. So we need actually two conditions, one on the domain, compactness, and one on F, which is continuity. Okay, so this is why this theorem is important, especially when it's really fundamental, because if you want to, in optimization problems, when you want to seek a minimum or a maximum, you need to make sure that it exists. And these two conditions, compactness and continuity, ensure the existence of a maximum and a minimum. Okay, so it's really a fundamental result, but mainly of theoretical interest. Okay, so now next result is something that you probably know from high school. It's called the intermediate value theorem. And here also I need two conditions. I need the fact that f be defined on an interval, actually closed, or yeah, it could be anything, but for simplicity I took a closed interval. And I need continuity. So what does this theorem say? It says that if f is continuous on an interval, then it achieves any value between f of a and f of b. So if y is between f of a and f of b, then there exists C in the interval whose image is Y. Now, there is a simple graphical interpretation, geometric interpretation of this. If we have a continuous function like this, then this theorem states that any horizontal line passing at Y, if Y is between f of A and f of B, then this horizontal line meets the graph of f. Now, the C here need not be unique, because if in this case, if we make y a little bit lower, then we get three solutions of the equation f of x equal y. Okay, so that is, when I say that it exists, it means that at least, okay, but it could be more than one point. So this is the geometric interpretation that you probably know. And once again, if we remove one of the assumptions, the result need not be true. So here's an example of a discontinuous function, right? And so of course f of b can be less than f of a. It's not really, so it's not really a big deal. Okay, so because I can invert this, but here y is between f of a and f of b, but the horizontal line does not touch the graph because I have a discontinuity point. So continuity is very important for, and once again, this is a topological result. Okay. Now, of course, if you work on it, if the domain of f is not an interval, for example, the union of two disjoint intervals, then of course you can check that it's not true. Okay. Now, there is another version which is equivalent to the intermediate version theorem. I call it version 2. It says that a continuous function takes an interval into an interval. So the image of an interval is an interval. And once again, this is not true for all functions. And now I'm not going to prove this version either, but if you like, you may prove that the two versions are equivalent. Right? And as a corollary, there is a very known corollary that if f is continuous and goes from a positive value to a negative value, or vice versa, then f vanishes at a certain point. Okay? So this criterion is very important in order to establish the existence of a solution to an equation. And we shall see examples and exercises. Okay, now next result, it's a little bit different from the result of your book, and we shall prove it next year in a very simple way. So in a simpler way than your book, actually. If f is strictly monotonic and surjective between two intervals, I and j, then f and its inverse are both continuous and both increasing or decreasing strictly. Now, you know, actually, you may know that a strictly monotonic function is injective. Okay, it's not difficult to prove. So actually, f is a bijection, but continuity of f and f minus 1 is not so clear. And this is something that we shall prove next year in a very simple way. It takes 3 lines. Okay. Now, I may assume that if I assume that f is continuous, then I know that from the previous theorem that from version 2 that j is an interval. Okay, but here I made the thing a little bit different. So we may assume continuity, but we don't need to assume continuity if I know that I and j are intervals of any kind. And now you go back to the notion of uniform continuity. So in the definition of uniform continuity, the delta depends only on epsilon. Okay, so the order of the quantifiers here is very important. So compare this definition with the definition of continuity at every point. The order of the quantifiers is very different, and this leads to very different properties. Okay, so what does this sentence mean? It means that I can make the difference. So for every x and y, if x and y is sufficiently small, no matter where x and y are distributed, the distance between their images can be made arbitrarily small. Okay, but the point here is that the delta does not depend on x or y. Okay, so this is why we call it uniform, because it works for all x's. Okay, and of course, which one is stronger, uniform continuity or continuity? Uniform continuity is a stronger condition. So uniform continuity implies continuity, but the converse need not be true. And now I will present some examples where the converse is not true. Okay, so I'll give examples and counterexamples. Okay, let us start with a trivial context. So the identity function is, of course, uniformly continuous. Why? Because you can just take delta equal epsilon. If delta equal epsilon and x minus y is less than delta, then x minus y is less than epsilon. So, right? So f of x minus f of y less than epsilon. So it's kind of trivial. And once again, we can replace less or equal strictly by less or equal. So same thing. Now, if we restrict 1 over x to the interval 1 infinity, and it's very important to work on this interval. So the domain is very important. Okay, because we shall see later that 1 over x is not uniformly continuous on 0, 1, but it's uniformly continuous on 1 infinity. And this is very easy because if I look at the difference between f of x and f of y, and they reduce to the same denominator, I get x minus y in absolute value divided by xy, and these are positive, bigger than 1. If x and y are bigger or equal than 1, then their product is bigger or equal than 1, so the inverse is less than 1. So we have this beautiful condition that f of x, f contracts distances, if you like. So the distances between the images decreases. Okay, so if this is less than epsilon, this is less than epsilon. So once again, I can take delta equal epsilon. Now let's trivial example. Radical x on 0 infinity on its domain. We know that it's continuous, but it's more than that. It's uniformly continuous. Why is that? Let me first establish an identity here. So radical of x minus radical of y in absolute value is less than the radical of the distance. Okay? Not completely trivial. Why is that? Okay. It's enough to prove this for x and y are strictly positive, because if one of them is 0, if y is 0, I get equality. Or if x is 0, I get equality. If both are 0, I get equality. So to prove that, it's enough to prove it for x and y both positive, because I need to divide now. Okay, first start with the triangle inequality. So absolute value of x minus y is less than absolute x plus absolute y, but since x and y are positive, I can write x minus y less than absolute value less than x plus y, and this is less than x plus y plus 2 radical. There's a 2 here missing, so x plus y plus 2 radical xy, and this is a perfect square, so it's radical x plus radical y to the square, so there's a 2 here. And so if I take square roots here, I get the square root of x minus y is less than radical x plus radical y. And now we divide by radical x plus radical y to get that the ratio is less or equal than 1. And now multiply by x minus y to the power 1/2, both sides. I get this. But now if you look at this left-hand side, this is what actually? An absolute value is what? Is actually radical x minus radical y, because this is the conjugate of radical x minus radical y. So the left-hand side is precisely equal to radical x minus radical y. And that's it. So the claim is proved. And now it's easy to conclude for the uniform continuity, because it's enough to take delta equal epsilon squared. Because if x minus y in absolute value is less than delta, then if I raise to the power 1/2, I get less than delta to the power 1/2, which is epsilon. If this is less than epsilon, this is less than epsilon. And this concludes the proof of the uniform continuity of radical x. Not trivial. Now let me give counterexamples. I will give two counterexamples. The function x squared defined on R is continuous, as we know, but it's not uniformly continuous. Why? Okay, take any positive number delta and consider two numbers x and y given by 1 over delta plus delta and 1 over delta. So the difference is delta. However, if you square, so x squared minus y squared, the 1 over delta squared cancel, and this is actually there's an error. This is 2 plus delta squared, but it doesn't matter because it's bigger than 2. So just square x squared minus y squared, the 1 over delta squared cancel, 1 over delta plus delta times 2 gives the 2, and there is a delta square. So this is a delta square, not a 1 over delta squared, but the change nothing. So what did we prove actually? We proved that there exists epsilon, which can be taken to be 2. So there is epsilon equal to, and for every delta there exists x, there exists y, whose distance is less or equal than delta, but the distance between their images is strictly less than 2. And this is precisely the negation of the uniform continuity condition, okay, which says for every epsilon there exists delta for every x, for every y, okay? Now, the function 1 over x is not uniformly continuous on 0, 1. So pay attention to the contrast. In the previous example, we took 1 over x on 1 infinity. So the domain is very important. When I say that a function is uniformly continuous, I need to precise where it is, on which set. So there's a contrast between this example and the previous example. Okay, so once again, take a positive number delta and take two numbers, delta over 1 plus delta squared and 2 delta over 1 plus delta squared. Of course, these two numbers are positive and less or equal than 1, because 2 delta is less or equal than 1 plus delta squared. And this is something that you may know from high school, because it's equivalent to saying that delta minus 1 squared is bigger or equal than 0. So now the difference between them is just delta over 1 plus delta squared, and this is less than delta because the denominator is bigger than 1. However, if you do the inverses, so you take 1 plus delta square over delta minus 1 plus delta square over 2 delta, you will get this ratio. 1 plus delta square over 2 delta, which is, once again, by the same reason, bigger or equal than 1, because I inverted it. So once again, we have proved the negation. So we found epsilon equal 1, such that for every delta positive, there exists x, there exists y, whose distance is less than delta, but the distance between their images is at least 1. So 1 over x is not uniformly continuous. It's continuous on 0, 1, but not uniformly continuous. Okay? And the reason why these two are not uniformly continuous is actually the same. It's due to the non-compactness of the interval. So here R is unbounded. And here F is not, the interval is not compact, and F tends to infinity at 0. Okay? And I will end this video with a positive result that I will prove next year. A continuous function on a compact set is uniformly continuous. So continuity implies uniform continuity in the special case where the domain is compact. And this is, so we need a topological condition, so to go from continuity to uniform continuity. Okay. So if you like, continuity is a local property. Okay, it depends on the point where the function is defined. Whereas uniform continuity is a global property. Okay, so this is an example where topology is useful to take us from a local property to a global property. Okay, so this concludes this video and chapter 3. I will post the exercises shortly online, and I will solve them next week. Okay, and we'll just have the last chapter that, okay, it's not difficult, it's a little bit computational, and I think we will finish on time. Okay, so thank you for your attention.